There is a moment in time that no telescope can see, no computer can simulate, and no human mind can fully comprehend. A moment so extreme, so violent, so impossibly dense, that the laws of physics as we know them simply break down. And here's what makes this terrifying. We have built the most powerful space telescope in human history, pointed it at the edge of the observable universe, and what it found is shaking the foundations of modern cosmology, because what's out there doesn't match what should be there. And scientists are starting to ask a question they never expected to ask. What if we got the beginning of the universe wrong? For decades, we've had a model, a beautifully constructed, mathematically elegant model that explains how everything, every galaxy, every star, at every atom in your body came from a single point of infinite energy roughly 13.8 billion years ago, the Big Bang. It explains the expansion of space. It explains the faint glow of ancient light still echoing across the cosmos. It explains why the universe is made mostly of hydrogen and helium. And for a long time, the evidence supported it almost perfectly. But science doesn't stop when the evidence fits. Science gets dangerous when new evidence arrives that doesn't fit. And right now, something is very wrong with the picture we thought we had. To understand what's breaking down and why it matters, we first need to understand how we built that picture in the first place. Here's a fact that sounds like science fiction but is completely real. When you look into deep space, you are looking into the past. Light travels fast, nearly 300,000 kilometers per second, but space is unimaginably vast. So when light leaves a distant galaxy, it takes billions of years to reach your eye. Which means when you observe a galaxy 12 billion light years away, you're not seeing it as it is today. You're seeing it as it was 12 billion years ago. The universe is essentially its own time machine. And using this principle, astronomers have been able to reconstruct a kind of cosmic history, a timeline stretching from the present all the way back toward the beginning. 3 pieces of evidence form the backbone of this timeline. First, the expansion of the universe. In the 1920s, Edwin Hubble discovered that galaxies are moving away from us, and the farther they are, the faster they're receding. Run that expansion in reverse, and everything converges to a single point, a beginning. Second, the cosmic microwave background radiation, the CMB. This is the faint afterglow of energy left over from the early universe when it was a superheated plasma of particles. It radiates in every direction, perfectly uniform, at a temperature just 2.7 degrees above absolute zero. It is, in essence, a photograph of the universe at 380,000 years old, and it matches Big Bang predictions almost exactly. Third, the distribution of light elements. Big Bang theory predicts the early universe should have produced specific amounts of hydrogen, helium, and a small amount of lithium through a process called Big Bang nucleosynthesis. Look at ancient stars across the cosmos, and the hydrogen and helium numbers match almost perfectly. This is why the Big Bang isn't just a theory in the casual sense. It is one of the most rigorously tested frameworks in all of science, but almost perfectly is not perfectly, and that's where things get complicated. In 2021, the James Webb Space Telescope launched into orbit. It was built for one primary purpose: to see further into the universe than any instrument in human history, to look back closer to the beginning than we ever had before. What it found has left cosmologists genuinely unsettled. According to standard cosmological models, the early universe was chaotic and diffuse. Structure, galaxies, stars, black holes should have taken hundreds of millions, even billions of years to assemble. Gravity needed time to pull matter together. That's not controversial, that's physics. But JWST is finding fully formed, massive galaxies existing just a few 100 million years after the Big Bang. Galaxies that are bigger, brighter, and more structured than they have any right to be. Galaxies that, by our current understanding, simply should not exist yet. And it's not just galaxies. JWST has detected supermassive black holes, objects with billions of solar masses lurking in the very early universe. Black holes of that size are supposed to grow slowly, consuming matter across billions of years. But these ones appear almost fully grown in cosmic infancy. The reaction from the scientific community has been carefully measured, but unmistakably concerned. So, some researchers have called it a real problem. Others have described the observations as deeply puzzling. One team published a paper with a title that included the phrase universe-breaking galaxies. That is not normal scientific language. And then there's a problem that has been sitting in the data for decades, largely ignored because no one had a clean answer for it. Big Bang nucleosynthesis is the process by which the early universe forged its first elements in the first few minutes of existence. The predictions it makes about hydrogen and helium are spectacularly accurate, but lithium is a different story. The theory predicts a specific amount of lithium-7, one of lithium's isotopes, should have been produced in the Big Bang. When scientists measure ancient, metal-poor stars that date back to the earliest epochs of the universe, stars that preserve the chemical signature of the primordial cosmos, they consistently find less lithium-7 than predicted, about 3 times less. This is known as the cosmological lithium problem, and it has resisted explanation for over 30 years. It's not a rounding error, it's not a measurement artifact that will vanish with better instruments. It is a persistent, reproducible discrepancy between theory and observation. And there's another layer. Some models of early universe physics predict that another lithium isotope, lithium-6, should be extremely rare in ancient stars, but certain measurements suggest it may be present in quantities far higher than expected. 2 isotopes, both wrong in different directions. And this tells us something important. Either our measurement of ancient stars is incomplete, or something happened in the early universe that our current models don't account for. Neither answer is comfortable. There is one more anomaly that deserves attention, because if it holds up under scrutiny, it would be the most destabilizing discovery in the history of cosmology. Certain ancient stars, when their age is calculated based on their stellar evolution, chemical composition, and luminosity, yield estimates that push uncomfortably close to, or in some cases, appear to exceed, the accepted age of the universe at 13.8 billion years. Now, to be clear, the uncertainties involved in stellar age calculations are significant. These estimates carry large error bars, and the most likely explanation is that the methods used to calculate stellar ages have systematic errors built into them. But the fact that this tension exists at all, that some of our oldest stars keep returning ages that crowd the boundary of cosmic time, means we need to either improve our stellar models, refine our measurement of the universe's age, or confront the possibility that something in our cosmological timeline is off. When multiple independent lines of evidence all point toward the same crack in the foundation, that is not noise. That is a signal. Here is what honest science looks like. You build a model, the model makes predictions, you test those predictions, and when the data doesn't match, you refine the model. The Big Bang framework is not collapsing. The evidence for cosmic expansion, the CMB, and the primordial hydrogen and helium is overwhelming and not in dispute. What we are seeing is something more nuanced and more exciting. The edges of the model are fraying, and fraying edges in science are not a failure. They are an invitation. They are the universe telling us, you are close, but you are not done. JWST is still collecting data. Cosmologists are actively revising early galaxy formation models. New explanations are being proposed for the lithium discrepancy involving resonance effects in nuclear reactions, or the role of stellar processes in destroying primordial lithium over time. The stellar age anomalies are being revisited with more precise instruments. The model is being stress tested, and that is exactly how science is supposed to work. We live in one of the most extraordinary moments in the history of human knowledge. A telescope orbiting 1 million miles from Earth is sending back images that are actively rewriting what we thought we knew about the cosmos. And the questions that are opening up are bigger, stranger, and more profound than the questions we thought we were answering. The beginning of the universe is not a solved problem. It is the greatest open question in all of science. And the answer, when it finally comes, will change everything. If this kind of deep science is what you want more of, subscribe and turn on notifications. Every week we go further into the unknown. The next video is already waiting for you.